You ever stop and think about how a computer, which, only thinks in tiny, separate little steps, can create something as smooth and continuous as the audio you're hearing right now? Or how a robot can move with this fluid grace? Well, the answer is this surprisingly simple idea. It's like a universal superpower that works everywhere, from the most basic code all the way up to the most advanced AI. So let's dive in and break it down.
Yeah, this is the big mystery we're going to tackle. Digital machines, at their core, are all about individual steps. On, off. 0, 1. But the world we experience is continuous, right? Sound waves just flow. Our movements are smooth. So how in the world do we bridge that gap? How does step-by-step, choppy processing end up feeling like a seamless flow?
To get to the bottom of it, here's our game plan. We'll start by talking about that illusion of continuous flow. Then, we're going to pull back the curtain and reveal the secret: chunking. From there, we'll see how chunks of sound make high-fidelity audio possible, and then how chunks of action help a robot think. We'll even see what happens when those perfect digital chunks run into messy reality. And finally, we'll wrap it all up by showing why this is truly a universal superpower.
So what is this magic trick? What creates this amazing illusion of a continuous flow from a bunch of separate little steps? Well, the secret isn't some ridiculously complex algorithm or a super-powered piece of hardware. Nope, it's a surprisingly simple and really powerful idea.
It's called chunking. That's it. That's the secret. Instead of trying to deal with the huge, continuous river of data all at once, you just break it into small, manageable buckets. You process one bucket, then the next one, then the next. And if you do it fast enough, to us, it feels completely seamless.
Now, what I love about this is the insight from a user on Stack Overflow. They just hit the nail on the head. Chunking is a concept, not a physical action. This is so important. It's not some function you call in your code. It's a way of thinking about a problem. It's a mental model, a logical approach to make massive tasks feel totally manageable. Okay, so let's get down to the nitty-gritty. In its absolute simplest form, maybe in a programming language like C, it would look something like this. Imagine you have a giant 500 kilobyte block of data. It's huge. You don't try to swallow it whole. Instead, you just tell the computer, hey, start at the beginning and just process the first 128 bytes. Okay, done. Now just hop forward 128 bytes and do the exact same thing. And you just keep doing that. Repeat that simple loop over and over until you've chewed through the entire block, one little chunk at a time. Super simple, right?
Okay, so that's the basic idea. Now let's see where the rubber meets the road. We're going to look at our first real-world application and see how this abstract concept becomes absolutely critical for anyone who loves high-fidelity audio. We're talking about a program called Camilla DSP.
This is just a perfect illustration of a concept in action. The entire audio processing pipeline is built around these chunks. So one part of the program, the capture thread, it just grabs a chunk of sound. It then passes that chunk to the processing thread, which does all the cool stuff, applies all your fancy EQs and filters. Then it sends the newly processed chunk over to the playback thread, which plays it right through your speakers. It's basically a digital assembly line for sound, and the whole thing is built on chunks.
But here's the million-dollar question. How big should a chunk be? This is the critical trade-off. See, if you use larger chunks, your computer's CPU gets to relax a bit. It doesn't have to work as hard. But you introduce a noticeable delay, or what we call latency. On the flip side, if you use smaller chunks, the response is almost instant, which is great, but you risk totally overloading your CPU. So it's this constant tug-of-war between performance and responsiveness, and finding that perfect balance is the real secret to flawless audio.
And this isn't just guesswork, right? The software's own documentation gives us a really clear guide. Just look at this. As the audio quality, the sample rate goes up, the recommended chunk size also goes up. The goal is always the same. Keep the processing time for each and every chunk in that perfect sweet spot. In this case, it's about 22 milliseconds, to make sure the playback is buttery smooth without just overwhelming the system.
All right, let's really take this concept up a notch. We've seen how chunking works for data, like a stream of sound, but what happens when we apply it to something way more complex, like the actions of an AI-powered robot? This is where the whole idea gets a serious upgrade. See, for this Pi-Zero robot, a chunk isn't just a block of information anymore. It's a plan. It's a whole predicted sequence of movements over the next few moments. The robot is literally thinking ahead in chunks of time.
And it thinks pretty far ahead, too. At any given moment, the Pi-Zero model predicts a full chunk of its next 50 actions. I mean, that's like planning out your next 50 footsteps before you even take the first one.
But here is the really clever part. It predicts 50 actions, but it only executes the first 20. So why would it do that? Well, because the immediate future is way more certain than the distant future. Those first 20 actions are the most reliable, the ones least likely to be wrong.
So what you get is this really powerful strategy for dealing with a world that's just totally unpredictable. The robot makes this big, ambitious long-term plan, that 50-action chunk, but it only commits to the safest, short-term part of it. After it does those 20 actions, it stops, takes a fresh look at the world, and generates a brand new 50-action chunk based on the new situation. It's this constant cycle. Plan, act, and replan. It's brilliant.
Okay, so we've got this incredibly elegant software strategy, this whole predict long, execute short chunking thing that lets a robot navigate uncertainty. So, why, with all this intelligence, are some seemingly simple physical tasks, like, say, folding laundry, still so incredibly difficult for robots?
A comment on Reddit just sums it up perfectly. Draping physics is a pain. The problem isn't the planning, it's the messy, chaotic, totally unpredictable physics of the real world, especially when you're dealing with soft, floppy things like a t-shirt.
And this really gets us to the hardware bottleneck. The software can generate these perfect chunks of actions all day long, but the robot is limited by its physical body. It might only have, as one user put it, 2 pinchers with really limited dexterity. And you know, the hardest part isn't even the folding itself. It's just getting the piece of clothing into a known, predictable starting position in the first place. The software is ready to go, but the hardware, it's still playing catch-up with the messiness of reality.
Okay, let's tie all of this together now. We've seen chunking in low-level code, in high-fidelity audio, and in super advanced robotics. We've seen its power, and we've also seen its limits. So what's the big takeaway here?
The main idea, the thing to really remember, is this. Breaking down massive, complex, or continuous problems into a series of small, manageable chunks is one of the foundational superpowers of all computing. It's how we make the impossible possible.
And this just lays out the journey we've been on so perfectly. The simple idea of a chunk started as just an address and a length in a computer's memory. Then it became a block of audio samples, carefully balanced for performance and latency. And then it evolved into this sophisticated predictive strategy for an AI robot, a whole sequence of future actions. It's the same core concept, just applied at a higher and higher level of thinking.
Which really just leaves us with one last question to chew on. This simple but incredibly powerful idea has unlocked so much, from audio processing to robotics. So what other complex systems, what other seemingly continuous flows in technology, or maybe even in our own lives, could be better understood and maybe even solved by breaking them down one chunk at a time?